All right, so some terminology. This question that I kept saying, am I guessing? Well, scientific reasoning starts with the assumption that there is no effect, that nothing is happening, that I must be guessing. In order to demonstrate an effect, we have to provide results that falsify that show that that this idea that I'm just guessing would be very unlikely given the kind of result that we got. So we need to demonstrate that it's unlikely that the result is true, or unlikely that the result would be true if the result would occur if the assumption was true, I should say. So assume that I'm guessing. Does that mean that I always get 50% correct? No, I think as we saw with the sampling distribution, it means that 50% correct is the most common piece, but certainly other things are relatively common as well, such as getting 6 right. So the big question we have to deal with is how far from 50% supports the claim that I'm not guessing? So one question we want to ask is, what would the mean score be that reflected guessing? Well, the mean score would be about 0.5. So how odd does that result have to be? I always like to use the analogy that statistics is like a jury trial. We begin with an assumption and we look for evidence that falsifies the assumption beyond a reasonable doubt. Now in court, that assumption is not guilty, and the evidence must show beyond a reasonable doubt that the defendant is guilty. Regrettably, in court, everybody uses a different criteria for reasonable doubt. And what exactly that means. Within statistics, we actually use a clear and defined criteria. So in science, very similarly, the assumption is that there's no effect. Or we could say, I'm just guessing. Evidence would have to show beyond a reasonable doubt that I was not guessing. So what is that reasonable doubt? What would be a surprising result if I were just guessing? So what exactly is reasonable doubt in a statistical sense? We establish criteria for the probability of a result. Most commonly in psychology, a result would have to occur less than 5% of the time. A result that would occur less than 5% of the time if that initial assumption of no effect was true. It meets the standard for reasonable doubt. Sometimes you could use 1%. Some people advocate for 0.5%, but 5%. The 5% rule is definitely the most common within psychology and other fields. So what exactly would be likely or unlikely in our example? So you can see all the different things that would happen. If I got 6 correct, 6 or more correct, generally we think of it in that way, that would happen pretty often. 6 or more correct would happen almost 40% of the time. 7 or more correct, that would happen about, looks like 18.1% of the time. 8 or more correct, that happened about a little over 6% of the time. 9 or 10 correct, that happened only about 1.1% of the time. So 9 or 10 correct appears to be where we would land in terms of meeting that 5% criteria. That is, I would have to get 9 or 10 right for you to say, okay, well, it doesn't look like you're guessing. Now, keep in mind, these are probabilities. That doesn't mean that 9 or 10 correct is impossible. 9 or 10 correct could very well happen, but it would be very unlikely to happen if I was just guessing. And you can see the different ranges of results that we talked about. So some formal terms. First, falsification. This is the logic of science. To support a claim, we must falsify or throw into question, at least, the opposite claim. To demonstrate I'm not guessing, I need to produce a result that demonstrates that would happen very rarely if I actually was guessing. Null hypothesis, very important term. In fact, this whole section is on null hypothesis significance testing. It's noted as H sub 0, and it's the initial assumption of no effect. It's a formalization of that assumption. We're actually going to put numbers and symbols on this. Alternative hypothesis, H1, that's the opposite of the null. For example, there is an effect. This is generally a very broad statement. And again, we'll put numbers on that. Alpha level or type 1 alpha or type 1 error rate. This is where we say, okay, this is how unlikely our sample result has to be to establish reasonable doubt. Typically, this corresponds to a probability of 0.05, although that is arbitrary, and many folks have argued for different rates. A couple of terms here. Reject the null hypothesis. This is what we do when we have a result that is less probable than that 5% result. When our probability of our result is less than what we specified as our alpha level. When we reject the null hypothesis, we can be reasonably certain the null is false. We know that 5% of the time, we might be wrong, but we're willing to take that chance. Fail to reject the null hypothesis, very important, that terminology. Decision made when the probability of our result is greater than or equal to whatever we've set alpha to. So if this were 5 point, if an outcome gave us had a probability of 0.051, that wouldn't meet below our threshold. Our sample result in this case would not be surprising if the null hypothesis was true. One thing to note here is I did not say accept the null hypothesis, because this is not evidence that the null is actually true. It is evidence that we don't have any reason to question the null. So we simply failed to find sufficient evidence to falsify the null. This is in no way providing support for that null hypothesis. So very important terminology there. We never accept a null hypothesis. Okay, so apply to our example. Our null hypothesis in terms of means, remember mu is the population mean. Mu is equal to 0.5. Note that hypotheses will always be about population values. The alternative hypothesis is simply the opposite of the null. It's not 0.5. Alpha set at 0.05, and this tells us we'll reject the null hypothesis if our result would occur less than 5% of the time when the null hypothesis was true. So why does this work? Well, it goes back to those sampling distribution things that we talked about. And more generally, what's called the central limit theorem. Given a large enough sample size, and that sample size tends to hover at around 30, a sampling distribution drawn from any population, regardless of its shape, will have a mean that's equal to the population mean and a standard deviation that's equal to the standard error of the mean. Practically, that means that these sample means are normally distributed. So we can use the properties of the normal distribution to calculate probabilities of getting certain sample means. And that opens up a wide range of tests for us, a wide range of things that we can do.